A card gets swiped in Ohio at 10. The same card in Lagos at 10:02. The same card again in Manila at 10:04. Any one of those alone is an ordinary purchase. All three inside 5 minutes is obviously fraud, but only if someone counts them inside those 5 minutes. Every job in this series runs once a day. A daily job catches this tomorrow morning, long after the money is gone. So, run the daily job more often, every 5 minutes. That's the obvious fix, and the reason it fails is the most useful idea in this episode. That job reads 90 days of history to compute its features. Run it every 5 minutes, and it rereads all 90 days every 5 minutes to produce an answer differing from the last by a handful of rows. You'd spend the whole 5 minutes rederiving what you already knew, then throw it away and start again. That's the split. A batch job recomputes an answer from scratch. What we need is one that maintains it, that already knows the count and only looks at what just arrived. Batch asks, what is the total each time? Streaming asks, what changed? And adds it to a number it's already holding. Before the mechanism, kill the model almost everyone starts with. Streaming does not mean a tiny job firing once per swipe, one row at a time the instant it lands. Spark has a mode that comes close. Essentially, nobody runs it. What actually runs is this. The stream is treated as a table that never stops growing, new swipes appended at the bottom. Against that table, you write exactly the query you'd write for a batch job. Group by card, count the last 5 minutes, as if it were sitting still. That's the whole trick. You describe the answer you want as if over a fixed table, and Spark works out how to keep it current from only the new rows. Same data frame API, same Catalyst optimizer, same executors as every episode before. Every few seconds, it wakes, takes whatever landed, updates the answer, and sleeps. That's a micro batch, small, frequent, still a batch. The engine never changed, it just runs in a loop now and remembers. So the fraud pipeline ends up with 2 jobs on 2 different clocks. The daily job still sweeps 90 days, building the slow features, typical spend, usual cities, patterns that only exist at that scale. Alongside it, a second job wakes every 30 seconds, touches only what arrived in those 30 seconds, and maintains the fast ones. Count in the last 5 minutes, in the last hour, spend in that window. 2 horizontal tracks. Top, labeled Daily Job, 90 days, with 1 large box and a calendar icon. Bottom, labeled Streaming Job, last 5 men, with many small boxes in a row and a stopwatch reading every 30 seconds. Which raises the question this episode turns on. The last 5 minutes by which clock? A swipe happens at a terminal at a precise moment. It's event time, stamped inside the record. Spark sees it later. It crosses a payment network, usually in seconds. If a terminal was offline, it can sit for minutes, then arrive in a clump. When Spark processes it is processing time. 2 clocks, and they drift apart exactly when it matters most. 2 parallel timelines. Top, event time, with swipes in neat order at 10, 10:02, 10:04. Bottom, processing time, the same swipes arriving jumbled, with the 10:02 one landing last and tagged late, a dashed line linking it back to its true slot above. Count by processing time, by when Spark happened to notice, and a flaky terminal dumping 10 backlogged swipes at once pours them all into the current window. The card looks like a fraud spree that never happened, while the window they truly belonged to was already reported quiet. So you window by event time, using the timestamp inside the record. Correct, and it creates a hard problem. If events arrive late, when is a window ever finished? You can't wait forever. Every open window is memory you're holding and an answer you haven't emitted. That's what a watermark decides. It's a promise you make to Spark. Once I've seen an event stamped 10:07, assume nothing older than 2 minutes before that is still coming. Windows ending before that line close, emit their counts, and release their memory. A swipe arriving after its window closed isn't quietly folded in, it's dropped. 2 minutes is a choice, not a fact, and it cuts both ways. A short watermark closes windows fast, holds little memory, and gets the number to the model quickly, but throws away more genuinely late swipes. And a dropped swipe is a fraud signal that never arrives. A long watermark catches the stragglers at the cost of memory that grows with every window still open, and a number that lags further behind. There is no correct watermark, only one that matches how late your data tends to be. A question about your payment network, not about Spark. And it sets your latency floor. A window reported once as a settled answer can only be emitted after the watermark closes it. That delay isn't a bug to tune away. It's the price of the guarantee. Now, where does the running count live between those wake-ups? The state store, a key value store alongside the executors, holding the partial answer for every open window, keyed by whatever you grouped on. Group by card ID, and every microbatch must route each new swipe to the exact task holding that card's count. That routing is a shuffle, the same one from episode 3, the same network cost that made wide operations expensive. Streaming gets no exemption. It pays a small shuffle every 30 seconds instead of one enormous one per day. And here, episode 10's lesson hits a wall. In a batch job, repartitioning is a free runtime decision. Try a number, watch the run, change it tomorrow. A stateful streaming query doesn't work that way. The number of state partitions is locked the moment the query first starts, because every saved state is filed by that count. Decide 6 months later you need more parallelism and raise it, and you haven't tuned the job, you've made its saved state unreadable. Plan that number before the first run, not after, which brings us to what happens when it dies, and a job that runs forever will die. Deploys, crashes, a bad node.
Everything just described lives in memory. So on a schedule, structured streaming writes 2 things somewhere durable: a log of which input it has consumed, and a snapshot of the state store. On restart, it reads that checkpoint, resumes from the last committed position instead of the beginning of time, and reloads every running count instead of starting them at 0. People assume that's where the guarantees end. It's where the last trap begins. Checkpointing does you exactly once on the way in. Spark won't reprocess committed input and won't skip any. It says nothing about the way out. Picture a microbatch that computes its counts, writes them to the feature store, then crashes a half second before recording it finished. On restart, Spark does the right thing, sees uncommitted input, reprocesses that batch, writes the results again. If that write is a plain insert, the card's count is now doubled downstream, silently, with nothing in the pipeline to tell you. The fix isn't in Spark, it's in the destination. Write with an upsert keyed by card and window instead of a blind insert, and the second write lands on top of the first rather than beside it. Exactly once isn't something Spark hands you at the end of the pipeline. It's exactly once processing from Spark plus an idempotent write at the other end. One without the other is a bug you haven't found yet. So streaming was never row by row and never a different engine. It's a query you'd have written anyway, run against a table that keeps growing, maintained instead of recomputed. Everything else follows from that one decision. You maintain an answer, so you need somewhere to keep it, the state store. Events arrive late, so you need a rule for when to stop waiting, the watermark. The job runs forever, so it will die. Checkpoints to resume, an idempotent write so the retry doesn't lie. Same 3 questions every time. How late is late? Where does state live? What happens if this batch runs twice? Next time, the finale. 90 days of history from the batch job, 5 minutes of velocity from this one, every feature this series has built. And the one thing none of it can do, approve or decline the transaction in the time it takes to pull a card from a reader.